Hey, it's Mr. K doing a problem for AP Physics 1. This is the second problem of our little quiz that we had today. And it is with our Sorta Earth. It's a cute little Earth. It's got a cute little satellite friend and only 4 trees. So we've got a planet that's sort of like Earth. It is more massive than Earth, three times as massive as the planet Earth, but only 2 times the radius of Earth. And what we need to figure out is what the heck is going on as far as the surface gravity is concerned on this planet. And so the way that we do that is we are going to kind of look at this equation, the Universal Law of Gravitation. The F is equal to big G m1, which is really the, I'm going to start it off on Earth itself. So m of mass of the Earth that we're on. M2 is going to be the mass of us. And that's just going to cancel out in just a second. You'll see why. And we're going to divide that by the radius of Earth squared. So this equation is going to be good for any 2 masses, and any distance between those masses there will be a force of gravity, no matter how big or small we're talking, it's still going to be there. Excuse me. And so really, if we look at this, this is equal to ma, and if it's us we're talking about, then the A is actually going to be a lot like G, and that is how we find our force of gravity. Now, that being said, if we just want to look at the gravitational field strength on this planet, we're going to take those M's of us, and we're going to take that away, and just say that G, which is known to be about 10 meters per second on our planet, about 9.8, but I like to use 10, and that's equal to all the stuff that's left over. So G, mass of the Earth, divided by the radius of the Earth, and we're going to square that. Alright, so really we're just looking at this stuff. So what in the world did... I just smudged it. But what in the world are we looking at in terms of the masses that we're changing? So we go to this planet. This is the formula for gravity, the gravitational acceleration on the surface of the planet. But we made something happen to M. So M is 3m the mass of the Earth. G is there. And we are doubling the radius. I'm going to put this... Make sure you use your parentheses. That's a very important thing. And we're going to say that's squared. Well, if you have a 2 inside of the parentheses, when you actually evaluate that thing, it's going to be 2r times 2r. So we have G, 3, the mass of the Earth, divided by 4, because that's squared there, the radius of the Earth squared. And so what does that do for us? That makes it so that if we rearrange it just a little bit, 3 over 4, G, the mass of the Earth, divided by the radius of the Earth squared. Well, that's oddly familiar. That's actually what we had back over here. So this thing is the same as this thing right here. So all that says is all this stuff is the same as all that stuff, and all that stuff is actually 10. So in the end, we have 3/4 is how we kind of change things, 10, and 3/4 of 10 is going to be 7.5. Hopefully we did that right. Meters per second squared. So if you go to this planet, although it is more massive and bigger than Earth, that actually does change the density of it. And so the gravitational acceleration is going to be 7.5. You're going to feel lighter on this planet. And about a fourth lighter than what you feel now, which would help you jump higher. Now, while the planet has a radius of 2r of the Earth, a research satellite of mass m, SAT, is in orbit around this planet with a radius of 3 times the radius of the Earth from the planet's center. Assuming in circular orbit, how fast does the satellite need to move to maintain its orbital radius? That's the second question here. And so you got this planet, you got this orbital radius for the satellite. It's going around that way, it's going around this way. And you need to figure out how fast that needs to be going in order to maintain that distance away from the planet and not get pulled in or fly off if you're going too fast. So really, the first thing that you should do is just say, hey, what forces are on that satellite? And if this satellite is in orbit, really the only force on it is this force of gravity due to this planet. Now, we need to figure out what that force of gravity is because, well, it's not going to be 3/4 that of the gravitational acceleration on Earth because the satellite's not exactly on top of the planet. It is another Earth's radius away from the planet. So, really, we're just going to work that same idea of G, and we have 3 times the mass of the Earth, just like before, but on the radius side, we are not double the radius now. As the problem said, we are actually 3 times the Earth's radius. So I'm going to put a 3 RE there. And we're going to square that. And so all things being the same as before, G is there, we got 3 ME there, but oh no, they're not the same as before. That 3 becomes a 9 R Earth squared. And so what this does for us is that's a 3 over 9, it's going to be 1/3. So this satellite experiences 1/3 the gravitational acceleration as it would on the surface of Earth. And so remember, all this stuff is actually 10. So what's 1/3 of 10? That's going to be about 3.33. So I might use this. I'm going to keep this around just in case. I'll just use that. But what you got to realize is what's going on as far as the speed goes. Now remember, the first thing that we did was we identified that this is the only force on it, and it is going in a circle. So if it's going in a circle, that means that this force, what is this force? This force is m of the satellite times a, or g in this case, and really the g is going to be 3.33. That force is the force helping it go in a circle. What do we call that? That's the centripetal force. So centripetal force is going to be mv squared over r. But be careful about this, because this r is the actual radius away from the center of the circle, and what we said earlier was that that was 3 times the radius of Earth. So I'm going to put 3 there, put a radius of Earth there, and if you're wondering which mass we're talking about here, it's the thing that's going in the circle. So this is actually mass of the satellite, so that goes away. And so if you wanted to find the velocity, then we need to, we need to move this over. Wait a minute, this is going to be even better. Let's not use 3.333, let's actually use 1/3 G m over r e squared, and that's all 10, right? Because if you do that, you see how we have a 1/3 over here and a 1/3 over there? Those go away. So I can do this. I can say velocity squared divided by RE is equal to G m over r squared. Now this is now your option. We need to solve for v. The thirds went away. We got a 1/3 there. You got a 1/3 there. Those just went away. We can either plug in the mass of the Earth and the radius of the Earth squared and all that stuff, or move that r over there, or we just remember that all this stuff was 10. Right? So let's move that r Earth over. We might end up having to plug that in. But that's not that bad. This v is going to be v squared, and I need to square root it. So let me just move over to the left side. The velocity that we're looking for is the square root of 10 times the radius of Earth. And from the board, I had it written down for y'all. 10, the radius of Earth is going to be 6 million something, 6.37 times 10 to the 6th power, and that's all under the square root. And let's see, that's just 6.37 times 10 to the, I'm going to use to the 7th because of that 10 over there. And then we're going to square root that body, and we're going to be at a velocity of 7,981,000 meters per second. So that's awfully fast. But yeah, you're in orbit, so you do need to travel awfully fast. About 7 or 8 kilometers a second for this planet. All right, we'll wrap that one up there.